Thank you very much for introduction. First of all, I'd like to thank the organizer, especially Paulo Santos, for inviting me to this conference. And it is my great pleasure to present our recent result at this opportunity. So the title of my today is quite aggressive. So some cavity quantum acoustics with a double quantum dot. And actually, we have not yet achieved in reaching to this cavity quantum acoustic regime, but I hope our results encourage you to study this interesting physics. So what we are actually doing is some working on a single or double, one or two electron system in a double quantum dot inside a surface acoustic wave phonon cavity. So I was quite impressed about the poster of the workshop. So therefore, I borrowed some central image in this my first page. Okay. So let me introduce some of our collaborators. Jason Chen who is my previous postdoc, who is now in Tarucha lab, and Yuya Sato, who is joining in this conference. And these two persons worked on low temperature measurement on double quantum dot. And they are my previous student who have worked on a surface acoustic wave characteristic. And my assistant professor Hashisaka made a surface acoustic device. And we have a strong collaboration with Dr. Koji Muraki at NTT Basic Research Lab. He provided us excellent two-dimensional heterostructure. So this is the outline. And I would like to give you some of our motivation on a phonon environment for semiconductor double dot, and some prospect for cavity QED, quantum acoustic. And next, in the second part, I will show you some technical stuff on how to fabricate a surface acoustic wave phonon cavity and device design, and how we have found a phononic bandgap in the Bragg reflector or localized cavity mode. Especially, we employed some time, frequency, and spatial resolved piezoelectric potential measurement. So in the third part, I will talk about some transport characteristic through a double quantum dot, where we study phonon-assisted tunneling and spin flip phonon-assisted tunneling. And I will discuss some Rabi splitting or expected vacuum Rabi splitting in our system. Okay, so we are interested in some dissipation problem in electronic state in a double quantum dot. So we have a lot of work in a coherent manipulation of the charge qubit on a single qubit manipulation or two qubit manipulation in those devices. The major source of dephasing comes from the charge noise in this device. But you can, if you play with some certain parameter space, you can find some sweet spot, or you could use some echo technique to overcome this dephasing problem. So then finally, the system is, the coherence is determined by the dissipation process, which is a phonon scattering in gallium arsenide. So because of these reasons, many people are interested in spin qubit system. So in the case of gallium arsenide double quantum dot, dephasing is practically determined by the nuclear spin fluctuation in the host material or charge noise in some cases. But many people are working on how to enhance the dephasing time. Some people can use some echo technique or feedback control of the nuclear spin fluctuation to make the dephasing time longer and longer. But of course, this dephasing time cannot exceed the dissipation time of the spin qubit. So in this case, again, it is determined by the phonon scattering and the spin orbit coupling for spin flip processes. So as these characteristics indicate that the electronic state in the double quantum dot is strongly affected by the phonon scattering process. So one of the strategies to overcome this phonon scattering problem is just replacing the material for smaller electron phonon coupling. But probably you cannot completely remove the phonon scattering. Another strategy we are interested in is that the artificially modifying the phonon environment. So if you could make some periodic structure in your host material, you can design a phononic crystal. If your phononic bandgap is adjusted to your qubit frequency, so there should be no phonon scattering exist in this material, artificial material. So another strategy can be making a phononic cavity in the phononic crystal. So then the quantum dot may emit a phonon to relax, but this phonon is confined in the cavity. So then this relaxed phonon can be reused or reabsorbed in the quantum system. If everything goes coherently, you can use various techniques developed in the cavity quantum electron dynamics, which can be called cavity quantum acoustic in this system. So towards this direction, we have studied some prototype of our device, so which is double quantum dot in a surface acoustic wave cavity. Of course, this metal grating works as a Bragg reflector, and we expect confined phonon mode, something like that. So let me give you some cavity QED effect. And in the weak coupling limit, the spontaneous emission from excited state to ground state is enhanced by the partial effect. If you go to strong coupling regime, the spontaneous emission and absorption takes place coherently, which induce finite Rabi splitting in the system. Some people are interested in ultra-strong coupling regime, where the rotating frame approximation breaks down. And then the vacuum state, ground state, previously unaffected, start to interact with finite photon state. So therefore, you'd expect some non-trivial vacuum state with virtual phonon.
Excuse me. Could you perhaps explain what are the parameters G0 and kappa? Sorry. So the meaning of this J0 and kappa and gamma.
G0 is a coupling between this and that, and this kappa and gamma is a loss of the qubit and the cavity loss rate.
The loss of the qubit and for
the loss of the loss of the two-level system. So I forgot which is which, but the other is a loss of the photon cavity. So, however, the conventional cavity QED is limited by the so-called fine structure constant limit. So if you consider a three-dimensional cavity, the normalized coupling constant, which is the coupling divided by the qubit frequency, is given by this formula. And you can find a fine structure constant here. Then if you use a three-dimensional cavity, the mode volume is always greater than cubic wavelengths. And your dipole, the size of the dipole is usually much smaller than the wavelengths. So therefore, the second factor with the mode volume here is usually much smaller than 1. So therefore, this normalized coupling constant is always much smaller than this fine structure constant. So in this direction, I should mention some recent developments of circuit QED. If you use superconducting coplanar waveguide, so this is basically the mode volume is proportional, just proportional to the lambda. So then this second factor can be close to unity. So therefore, some people have already achieved the significant, really large coupling with this scheme. So if you use LC resonator, this is basically the mode volume is independent of the wavelengths anymore. So some people already achieved a very ultra strong coupling regime with this LC resonator. So let me think how large strong coupling you can achieve with the acoustic cavity QED. So let me think about the three-dimensional phononic cavity. So in this case, also the mode volume is greater than the cubic wavelengths, but this wavelength is much, much smaller than the wavelengths of electromagnetic wave, the 5 orders of magnitude smaller than the wavelengths of the electromagnetic wave. So therefore, you have a chance to make a very, very small cavity with this acoustic system. That is a great advantage of using acoustic cavity QED. Of course, the drawback is that the relatively small electromagnetic coupling constant. So this k square is defined by the electric field energy divided by the total energy, mainly elastic or kinetic energy of the elastic wave. So if you consider the normalized coupling constant in the same way as the standard cavity QED is considered, then you can define effective fine structure constant. So in this case, this effective fine structure constant is no longer a physical constant, but involves some material parameters. So yeah, so the second part is involves a mode volume. This is basically similar to the previous case. So this effective fine structure constant is 1/13 in gallium arsenide. So therefore, gallium arsenide acoustic devices has little advantage as compared to the standard electromagnetic cavity. But because this is a material constant, you can find a better material, for example, zinc oxide or some other material we have seen in these conferences. So yeah, so in case with gallium arsenide, we have expect some little advantage, but maybe worthwhile to find a better material for this direction. Another important factor is that you should be able to fabricate a relatively small volume comparable to the cubic wavelengths. So for these directions, there are many studies on making phononic crystal cavities. For example, if you make a periodic holes or something, you can design your bandgap, and if you place such a phononic crystal here and there, you can design a phononic crystal cavity. So in this particular example, those people find a reasonably high quality at gigahertz frequency range. Or if you make a design of the hole to have a relatively small mode volume, which is comparable to the cubic wavelengths. So therefore, if you combine these techniques, there is a chance to have a relatively small mode volume at reasonably high frequency. So, however, for the cavity quantum acoustic purpose, we have to have some active device or double quantum dot in our case, inside the surface, inside the phonon cavity. So that is the reason why I chose the double quantum dot coupled with the surface acoustic wave phonon cavity. Okay, so I will move on to some technical detail of our surface acoustic wave phonon. As already heard many times about the surface acoustic wave, this is the elastic wave confined near the surface, and its lateral displacement and piezoelectric potential is within the lambda from the is concentrated within the lambda from the surface. So if you assume a 3 gigahertz frequency, the corresponding wavelength is 800 nanometer. In this case, the typical two-dimensional electron gas, 100 nanometer from the surface, is located somewhere here. So therefore, the two-dimensional electron system has a relatively strong coupling to the piezoelectric potential. That's a very nice coupling. So we want to have a standing wave to create a standing wave motion inside the cavity. As this animation shows, the node for the vertical displacement and the node for the lateral displacement appears at different positions. So we want to put a double quantum dot at the maximum electric field or node of the potential wave. So that is a requirement for in designing of the surface acoustic wave cavity. In our case, we used a metal array patterned on the gallium arsenide surface. So typical reflection coefficient at the edge of the metallized region is just a few percent. Of course, if you increase the height, larger reflection coefficient is expected. But if you make 100 of pairs, then total reflection coefficient of the Bragg reflector becomes close to unity. So you can make a quite nice Bragg reflector. So then this reflection opened a small gap in the dispersion relation of the acoustic phonon. And yeah. And another thing you have to consider is some velocity shift in the metallized region, which is typically 1 or a few percent change in the typical metallized region. So these prefactors are proportional to height divided by the wavelength is some known as material parameters. So if you find good material combinations, you will have a larger reflection coefficient. So we already know that such surface acoustic wave resonator has been commercialized for making high frequency filters or some sensors. However, these SAW devices are mostly fabricated on a highly piezoelectric material like quartz or lithium niobate or something. So there's not so many cavity report on gallium arsenide substrate. So therefore, we start working on the surface acoustic wave cavity, but just by patterning the titanium gold on top of the gallium arsenide substrate. And we made a pair of Bragg reflectors and with a small gap to make a phonon cavity. And half of the left Bragg reflector is shared with the interdigital transducer to electrical access to the surface acoustic wave cavity. So we measure the reflection spectrum by using vector network analyzer, and you can see two peaks. So one peak whose frequency is changing with the variation of the gap is the cavity mode. And another peak at here is a so-called IDT mode. Usually IDT is expected to appear at a wavelength matched to the period of the metal grating. However, this frequency is located at the middle of the band gap. So therefore, no phonon can escape from the central region. So this accumulated wave just returned back, reflected back to the power supply. So therefore, there is no signal at the center of the band gap. So instead, the IDT works at the edge of the band gap. So in this case, it is seen at the right edge of the band gap. So from this spectrum, you can identify the edge of the band gap by observing this IDT mode. And if you extrapolate this cavity mode to somewhere here, you can find the other side of the band gap. So this characteristic is also reproduced in the numerical simulation based on the one-dimensional coupling of mode analysis. So from this experiment, we can see how much the phononic band gap is realized in this material.
In the previous slide, when we think gap was 0.5, 0.4, what's the unit? Is it micron?
I think it is half lambda, the period of the grating. Okay, so let me see. Yeah, okay. So we also developed a technique to measure the piezoelectric potential inside the cavity by using a quantum point contact. So we have, again, the two Bragg reflectors, but these are well separated, separated by maybe 150 micrometer or something. The left Bragg reflector is shared with interdigital transducer to launch the surface acoustic wave burst wave. So this burst wave goes back and forth between these Bragg reflectors, which can be probed by the point contact potential detector. So for this purpose, we applied a burst RF wave to the IDT to generate a burst surface acoustic wave, slightly broadened surface acoustic wave burst wave. So here n is a number of period in the burst wave, and m is a number of period in the IDT. So totally we expect n plus m period of burst wave in the cavity. So this burst wave goes back and forth. So detect the piezoelectric potential at each quantum point contact. We applied another burst wave to the bias voltage of the quantum point contact. So this demodulate the surface acoustic wave. We expect a DC current proportional to the time integral of this applied demodulating bias voltage, and the piezoelectric potential, which modulate the conductance of the quantum point contact. So yeah, in this way, you can translate the piezoelectric potential to the DC current. But if you measure this detection current as a function of the delay time between injection burst and the detection burst, you can see such oscillatory current trace as a function of the delay time, which approximately measure the piezoelectric potential inside the cavity. So this method is quite informative in various surface acoustic wave characteristics. So this is the representative data. So here the detection current, which is normal derivative respective to the delay time, is shown in the vertical scale. So this detection current actually oscillates with the delay time, but in the central panel, you can only see the envelope function. So you can see a very large signal at the 0 delay time. This is just a crosstalk between here and there. So we should neglect this electromagnetic crosstalk. The direct surface acoustic wave can be seen in this wave packet. If you zoom in this region, you can see that this is oscillating with the time. So you can do the same thing for various quantum point contact. You can see the phase evolution from QPC1, 2, 3, 4. This clearly indicating that the surface acoustic wave is coming from the left side to the right side. So just traveling from left to the right. The reflection from the right Bragg reflector is expected in this time window. And if you zoom in the signal somewhere here, you can see a phase evolution, in this case, from point contact 4, 3, 2, 1. So this makes sure that it is really reflecting, the wave is coming from the right-hand side to the left-hand side. And if you in the same way, if you measure at this timing, we see a right-moving wave. So in this way, we can see surface acoustic wave packet going back and forth between the two Bragg reflectors.
So where's the amplitude in the middle smaller than on the right?
This is smaller. Yeah, so sorry?
Well, when you traverse the first time, the amplitude should be maximum of your oscillations. No? This measures basically the strength of the filter.
Yes.
So when it comes back, it probably attenuates a bit. And when it goes to first,
Yes. Yeah.
it doesn't seem to.
Yeah. Okay. Your question is: this is large. The right-going wave is larger, but the left-going wave is smaller. Yes, we do not actually analyze this yet, but probably so this Bragg reflector works as a internal reflection. So there is a lot of internal reflection here. So therefore, if you forget about this reflection, there is a slowly decaying wave is coming. So if you consider these to sum, so there might be some destructive interference happening.
There is no direct electric crosstalk to the other gravity system?
We haven't confirmed this, but based on the timing, this is a timing where the wave packet is just reflected back and arrive at this quantum point contact. Your question?
This was my question.
Okay, so this is a similar data set, but taken for a longer period. Actually, this multiple reflection appears at a very, very long time. And at this time delay, the total traveling distance is already 2 millimeters. This clearly indicating that the surface acoustic wave has a long, can travel a long distance without dissipating. So we can do a similar measurement at various frequency, the carrier frequency, I mean. The previous measurement was taken at the resonant frequency at here. But if you change the frequency just by 20 megahertz, the envelope didn't change so much. But if you change the frequency by 80 megahertz, those reflection signal completely disappears. So you can see a little signal somewhere here, but probably this is happening because of the reflection at the etching step, which has a relatively broad spectrum. However, the direct surface acoustic wave is still remaining here. So if you measure this spectrum carefully, so its frequency spectrum is summarized in this view graph. So this is the frequency spectrum of the direct surface acoustic wave, which the width is basically determined by the number of burst wave and the number of IDT, some Fourier spectrum of the burst wave, basically. However, the signal at those reflections has a sharp cutoff at those frequency. So this clearly demonstrates the Phonon bandgap in the Bragg reflector. So this can be compared with the numerical simulation of coupling mode theory, and the similar some reflection time domain reflection signal and the frequency spectrum are reproduced in the simulation, from which we can deduce the band gap of this Bragg reflector. So in our case, the typical Phonon band gap is just 3 or 4% of the central frequency. Okay, so if you measure just a continuous wave measurement on the same device, we see a little complicated patterns. When I saw these patterns, we didn't understand what was going on. But now we can say that this multiple peaks is associated with multiple cavity mode with this relatively large surface acoustic wave cavity. So now we would like to go to the single mode surface acoustic wave cavity with a relatively narrow gap, which accommodates just a single mode, something like that. So this summarizes the characteristic. We perform the same time-resolved measurement technique, and by which we can clearly separate the electromagnetic component and the surface acoustic wave component. So the burst wave is already cut at this timing, but the remaining part is just surface acoustic wave dissipating from the cavity. The typical cavity decay time of this particular device was 25 nanoseconds. And if you measure the spectrum of this amplitude, we can see the quality factor of 240. It's not very large, but this is smaller than the band gap of 3%. Yes?
These measurements are from the room temperature. And then one question that is, what is the aperture of your fingers?
This?
Yeah.
I don't remember exactly, but maybe 50 micrometer or something. Okay. So this quality factor is actually determined by the just a loss, or the this number of period was not sufficient enough. So, but anyway, we characterize the spatial distribution by using 5 quantum point contact. So in contrast to the previous traveling wave characteristic, we see a standing wave characteristic. So if you measure at the piezo-potential at 5 locations, we see an identical phase for the 1, 2, 3, 4, fourth QPC, but you can see an opposite phase at the 5th QPC. This indicating that the node is located somewhere between QPC 4 and QPC 5. So if you plot some normalized amplitude, you can see some part of the mode, surface acoustic wave mode inside the cavity. So this clearly demonstrates the spatial distribution of the standing waves. That is nice. But unfortunately, the node is located here. What we wanted is a node located at the center of the quantum dot. Probably I misunderstood the polarity of the reflection coefficient. So therefore, the characteristic was nice, but unfortunately we cannot use this device.
See, the previous slide, do you understand why this potential time dependence is really skewed?
Asymmetric?
Yeah.
I don't know. I don't know. So we made a second generation device with many stripe to increase the quality factor. So the peak width gets 10 times narrower. And we find that the phase evolution of the 1, 2, 3 is the same, and the phase on the 4th and 5th point contact is the same, and the node is located almost in the middle of the structure. That's what we want. So, however, we see 3 peaks. We do not know actually what is the reason for that, but this could be related to some complicated patterns for defining double quantum dots. So, but anyway, we focus on the largest peak, number 1, which shows this nice spatial resolution, evolution of the mode.
Excuse me. So in the previous slide, you had this horizontal gate. Just to define the double dot, or is there also some capacitive coupling intended?
Yeah, actually, I wanted to study a couple double dots, but at the moment we only activated one of the double dots.
Okay, but you don't. But to the IDTs, basically, you don't need the capacitive coupling. It's not really necessary.
Sorry, capacitive coupling to be here and there. Yeah.
Only to the two double dot systems, and it's just handy to use those lines for energizing them.
Yeah. So yeah, we only need just a single double dot is necessary for the first experiment, but just in case. So this is a quick summary of our cavity characteristic. The Phonon bandgap, something like that, and cavity resonance or Q value, something like this. The important parameter for cavity is finesse, so which is 80. So that means the surface acoustic wave goes back and forth 80 times before escaping or dissipating to somewhere. So the resonance frequency is around 3 gigahertz, whose phonon energy is something like that. And if you cool in a dilution refrigerator, the thermal excitation of the phonon can be much smaller than 1. Yes.
So just lost one point. So your fingers for the mirror are placed also on top. So is there two depth below the fingers, or you actually everything on top of the okay.
How do you find the Phonon bandgap though? The first thing, delta FBI.
Yeah.
How is it defined?
This is shown in this picture. Okay, so I move on to the transport characteristic of the double quantum dot. So as already Wilfred introduced, we have made some inelastic tunneling spectroscopy in a double quantum dot. So if you if you measure the current as a function of the energy detuning between the two quantum dot levels, so you see elastic peak at the 0 detuning here, but we always find a large inelastic current on the emission side. So of course, if you change the bias polarity, same spectrum appears on the opposite side, which indicate that the energy is lost by emitting phonons. The interesting observation is that you can see a little bumps in the spectrum, which is also reproduced in the reversed bias, and also is by changing some other conditions. So these bumps are magnified in this plot, in the log-log plot. And the energy of this bump is larger with smaller quantum dot, double quantum dot, and there are smaller energy appeared smaller energy with a larger quantum dot. So this characteristic can be understood as a phonon resonance because the phonon scattering matrix element is maximized when the distance between the two quantum dots is matched to the half of the wavelength. So this is the reason of the phonon resonance. But of course, the phonon wave vector can be arbitrary directions. But if you sum up all possible configurations, the theory suggests still visible bump structures in the calculated curve. So therefore, we believe that they are associated with the phonon resonances. And so these energies are consistent with the bulk or surface acoustic wave dispersions. So there might be some phonon contribution to this, surface acoustic wave contribution to the phonon resonances. So to prove this surface acoustic wave coupling to the quantum dot, we employed surface acoustic wave measurement, and we launched a surface acoustic wave from interdigital transducer and irradiate to double dot to induce a transition from the left dot to the right dot, for example. So this is a typical phonon-assisted tunneling characteristic. Unfortunately, the width of the peak is a little bit larger than the phonon energy. So therefore, we cannot resolve the individual phonon-assisted transitions. But you can see some wiggle associated with a 2HF spacing. This is because that the phonon-assisted tunneling has a Bessel function dependence at some particular amplitude. And then, for example, the middle of the peak can be smaller than the two adjacent peaks. So that is the reason why you see a 2HF period of modulation in the current spectrum. So, and important thing is that the in this multiple phonon absorption or emission processes, and you can absorb or emit some integer number of phonons to the phonon field. So we performed the same experiment for the double quantum dot inside the surface acoustic wave cavity. So this is the result of the phonon assisted tunneling. In the similar way, again, the width is not very, is almost same as the HF. Now HF is 13 microelectron volts, but anyway, so you can see a similar oscillatory behavior in the current spectrum, and which appears at the energy detuning, which is integer multiple of the phonon energy. So we can also use the Bessel function or photon or phonon-assisted tunneling theory to reproduce this current spectrum, and we see a quite nice agreement with theory. So we can say that this is a phonon or photon-assisted tunneling spectrum. So how?
In this case, the inelastic tunneling is much deeper in the lowest curve than for the old measurement. Is this because of different body couplings, or what is the reason?
Yeah, because in this measurement we have chosen very small tunneling coupling to reduce the peak width. So that's why the inelastic tunneling cannot be visible, cannot be seen. So, however, we know that there is a crosstalk from the IDT to the quantum dot. So this is not purely from the phonon, but there is some combination of the phonon and some electrostatic crosstalk, some photon contribution. So in order to separate the photon and phonon, so we performed some time gating technique. So we, instead of the continuous wave in the previous experiment, we applied a burst surface acoustic wave. Sorry, the burst RF wave to the IDT. And of course, the crosstalk is just instantaneous and appears only for this period. But the surface acoustic wave is accumulated in the cavity, and which has a longer decay time. So therefore, there is a surface acoustic wave contribution only for this period. So in order to separate this and that period, we applied some square voltage pulse to this region, which works as a kind of in-plane gate, and which split the resonant peak into two. So we focus on this peak, which measure the surface acoustic wave signal only. So if you change the carrier frequency, so you can see broadening or splitting of this peak even in this period, and this clearly indicating that the surface acoustic wave phonon contribution at this frequency. So now we repeat the same measurement, but in the so-called Pauli spin blockade regime to see a spin flip phonon assisted tunneling. So let me explain how the Pauli spin blockade works. So we focus on the 2-electron double quantum dot and consider tunneling transition from 1-1 charge configuration and a 0-2 charge configuration in the double quantum dot. But the tunneling between here and there is allowed only for singlet spin correlation because of the Pauli exclusion principle in the right quantum dot. So therefore, if you apply a large bias voltage to the double quantum dot, then the system will be stuck by one of the triplet state, and the current remains low level. So that is the Pauli spin blockade effect. So if you change the energy bias between these two levels, those energy state changes something like that. Because of the tunneling, 1-1 singlet and 0-2 singlet shows anti-crossing behavior. So the Pauli spin blockade prepares the electron in one of the triplet state. So then we irradiate a surface acoustic wave to excite electron in the triplet state to higher lying 0-2 singlet state, or relax the system to lower lying 0-2 singlet state by phonon. Because there is a inhomogeneous nuclear spin polarization and spin orbit coupling mechanism in the quantum dot, so such spin flip transitions are allowed. So, so in our measurement, we focus on the zero field Pauli spin blockade, where all triplet states are nominally degenerated. This is very convenient because all possible transitions are expected at the same detuning conditions. So we start from showing the standard Pauli spin blockade characteristic. So if you change the two gate voltage in the two-dimensional sweep, you can clearly see a Pauli spin blockade region in this trapezoid region. This tiny peak along this line corresponding to the energy alignment of the 1-1 state and the 0-2 state. But this finite small, by the way, this is taken at the finite magnetic field, where the Pauli spin blockade can be can be seen very clearly. So this little peak is associated with some hyperfine coupling. So this is the schematic energy diagram of the 2 electron state in the presence of the Zeeman field. The peak here is associated with the energy crossing of this triplet state to the singlet state, which induce some electron spin, nuclear spin free processes. So that is the reason why the current is a little bit increased. So if you change the magnetic field, the current is maximized at these conditions. So this is a condition where the Zeeman splitting coincides with the tunneling coupling. So from which we can estimate the tunneling coupling in a double quantum dot. But in this case, we will focus on the zero field spin blockade. In the case of zero field, zero magnetic field, all triplet states are degenerated, and which effectively couple to this singlet state by the very small amount of nuclear spin fluctuation here. So therefore, this coupling lifts the spin blockade. But therefore, spin blockade works only in the around zero detuning region. So that is the reason why you see a dip here. So this looks like a double peak, but I think this is not a double peak, but just a dip in the central of the large resonant condition. So now we zoom in the center of the spin blockade region and irradiate the surface acoustic wave cavity. So then we see a current peak around here and around up there, which are almost separated by 2HF, which can be explained by this phonon spin flip phonon assisted tunneling. That's very nice. And if you increase the power, of course, the current becomes larger. Larger and larger. And if you increase the power much more, these two peaks merge into a single peak. And the second two phonon process start to appear. So since there is a small valley here, so I think this merging is not a simple broadening of the peak, but I think this two peaks is merged into a single peak. So this characteristic can be understood by considering the Floquet quasi-eigenstates. So here I plot the Floquet eigenstate, but we consider a random Oberhauser field which slightly lift the degeneracy of 1,1 triplet states. And we consider the tunneling between the two dots, which shows the anti-crossing behavior at here. So we applied time-dependent term on the oscillating detuning for the surface acoustic wave, which induce a phonon sideband here and there, so which are separated by basically HF. So we are in this measurement, the spin blockade phonon-assisted tunneling appears at the crossing of the triplet state to this phonon sideband. So our signal is expected at this crossing. So, on the other hand, you can also see some finite Rabi splitting in the theoretical calculations. And if you increase the power, so the alpha is a normalized amplitude of the oscillating potential, which So if you increase the power, the Rabi splitting also increases. As a result, this crossing point shifts inward. And finally, if you increase the power at some the specific condition where the zero phonon coupling vanishes, the crossing point appears around the zero detuning conditions. So this effectively explains why the two independent peaks merge into a single peak. Okay, so we also performed some numerical calculations by using Floquet-Lindblad master equation. And in addition to the previous Hamiltonian, we considered some dissipative process of coupling to the lead or cotunneling or dissipation or dephasing or something. And by solving this master equation, we can reproduce the zero field spin blockade in the upper panel. And if you zoom in the central region, and if you increase the RF amplitude, the spin flip phonon assisted tunneling is also reproduced. And these two peaks merge at a single peak, which also consistent with our observation. And again, I should mention that this is measured at the continuous wave. So therefore, there's two contributions from phonon and electrostatic crosstalk. So, so unfortunately, we were not able to perform the time gating technique for this measurement, but instead I'd like to show you some frequency dependence. So this is the current as a function of the IDT amplitude for different frequency at on resonance and off resonant conditions. You can see a significant large current on resonant conditions. So this is a plot of the peak shift of this peak, and which decreases more rapidly as on resonant conditions as compared to the off resonant conditions. So therefore, there is a significant Rabi splitting from induced by the phonon surface acoustic wave phonon field. So let me estimate how much Rabi splitting is expected. So since we all know the tunneling coupling, the maximum Rabi splitting is expected to be something like 5 microelectron volt. So we have no experimental estimate of the Rabi splitting, but we can do some crude estimate by assuming a mode volume of 1,500 cubic lambda, which yield the vacuum splitting of 7 megahertz. So unfortunately, this is not sufficient enough to resolve in our experiment, but by making a much smaller mode volume cavity, so I expect the vacuum Rabi splitting can be enhanced significantly. So in summary, we talked about some surface acoustic wave cavity and phonon assisted transition, including some spin flip or without spin flip process in the double quantum dot. So this measurement encourage for studying cavity quantum acoustics. So thank you very much for your attention.
Thank you very much for the nice presentation. We already had some questions during the talk, but there's more questions.
So in your device, you have IDT on one side. Yes, right. So if you put IDTs on each side, and by playing with the case of the microwave drive, can you cancel the crosstalk at the quantum dots, and then still drive the surface acoustic wave?
Yeah, I think basically you can do that, but I have never tried that.
More questions? model.
So is this effect of the speed flipping, do you know where it comes from? Is it a pure electric effect, or is it?
Yeah, this is due to the nuclear spin fluctuations. So we are working on the zero magnetic field. I'm sorry. Sorry, I don't find good figure. So we worked on that at zero magnetic field. All triplet states are more or less degenerated, but the random spin nuclear spin orientation gives us some effective magnetic field oriented at different positions. So in this case, if the energy is already matched, there is no spin flip. The quantization axis in one dot and the other dot is already different. So this is the case the spin blockade is already lifted. But the spin blockade in the central region is held because of the large exchange energy. So this is the case that the singlet and triplet basis works well. But if you compensate this exchange energy by the surface acoustic wave, which can lift the spin blockade.
Which kind of coupling do you need in this chart to be possibility to reach strong coupling? So what is your dephasing time of your
Sorry? What?
What is the dephasing time of your system?
Dephasing time.
Nanosecond, 100 picosecond?
In this particular measurement, it is determined by some electric noise, mainly coming from the RF line. We didn't care much about this external noise in this measurement. That is the cause of the relatively wide elastic peak.
Okay, so there's no more questions. I think there's one more question.
So what would be the most straightforward way in your system to increase this vacuum Rabi splitting?
Straightforward.
The splitting, vacuum Rabi splitting was 7 megahertz or so?
Yes.
So what would be the most straightforward way to increase?
Design, we need a more larger reflection coefficient, yeah, actually. Yeah. By changing some material or thicker metal or increasing the frequency